Hello everyone, welcome back to the channel. In this video we are going to see a pretty interesting property of prime numbers, that's again in number theory. So we're saying that if p is a prime number greater than 3, then p when divided by 6 is congruent to 1 or 5. That means when p is divided by 6, we get a remainder of either 1 or 5. So we are about to prove this formally. So like I usually do, I would start with some examples of how P can look like to get a visualization of things. So P will definitely belong to the set of prime numbers greater than 3. So I cannot write 2 and 3 here. I have to start my writing the set of prime numbers greater than 3. So that's 5, 7, 11, 13, 17, 19, 23, 29, and so on. This goes on. This is a countably infinite set. Like I have explained in some other videos of perfect squares. This is similar. But then I have something to prove with mod 6, so I can just start taking individual values of p. So 5 is congruent to 5 mod 6. 7 is congruent to 1 mod 6. 11 is congruent to 5 mod 6. Or sometimes this remainder is also called minus 1. Because if 6 is leaving a remainder of 5, you can also say it's like minus 1 from the next 6. Next multiple of 6, minus 1. So anyway, we are gonna call it 5 here, because that's easier to understand. So 11 is 5, 13 is a remainder of 1 mod 6. Just gonna write it down for is a remainder of 5 mod 6. Leaves a remainder of 1 mod 6. 23 leaves a remainder of 5 mod 6. And finally 29 is congruent to 5 mod 6. So we can already see that the property we are about to prove is valid, but we are now gonna, instead of looking at exact values, we are gonna present a formal generalized proof. And to do that, one of the elegant ways is to use something that's called exclusion or exhaustion. Exclusion exhaustion is kind of similar, where we exhaust all the possibilities of whatever can be a prime number. But to do that, I will first define that to be a prime number greater than 3, a prime number is already, so if this set is P, capital P, if this set is capital P and the prime number belongs to this set, then the set of prime numbers is a subset of the set of all positive integers. It's a subset. Now, not all prime numbers, not all positive integers are prime numbers, but if you have a prime number then greater than 3, maybe I should have called it p greater than subscript greater than 3 or something. Anyway, just simply p. Then any prime number of this form greater than 3 is also a positive integer. Now, if I try to visualize how the set of positive integer looks like, it looks like what we already know. This goes on to infinity. Both are infinite sets, countably infinite sets. So P is kind of a subset of Z plus. So if I define an element of z, small z element of z plus, sorry. So small z is one positive integer that may or may not be prime. Okay, it's just one small positive integer. But if I'm saying small z, firstly I'll also define. So I'm defining two variables here, two elements of two sets. Z is any positive integer and p is a prime number greater than 3. So every p will be a z, like every p has to be mapped to a z, but not every z is necessarily a prime number or necessarily greater than 3. It could be 2. So I'll define z first. So this gives us an idea that p is kind of the smaller, since p is a subset, p has less values and z has more values. So if I'm trying to use exclusion or exhaustion, if I'm trying to exhaust all possible options, I will have to exhaust z and not p. So z can be defined as, maybe z is converted to a mod 6. I'm introducing this because I have something to prove on P with mod 6, but I have to exhaust Z, so I'm defining Z as if it leaves a remainder A when it's mod 6. Now, from the property of modular arithmetic in number theory, when a number is divided by n, it can only leave a remainder from 0 to n minus 1. So 6 can only leave remainders from 0 to 5. Nothing else, because now of these remainders, we are saying that if z is prime, then you can only have these two remainders and nothing else. So that's what basically we have to prove. If you have any other remainder, it's not prime. But firstly, is this a basis that can span z plus entirely? Now what I mean by this is, okay, firstly, what is a basis? I'll define z belongs to a set, let's call it 6n, 6n plus 1, 6n plus 2, 6n plus 3. I'm just taking the remainders from here. Sorry. 6n plus 4 and 6n plus 5. Gonna call this set, I'm gonna call this set 6s, so SC or something. Now it's very important to note that SC, since it is general, like n is a positive integer here, or n is just an integer, n can be an integer. So if I choose certain values of z, then this SC set can form a basis to span C plus. What I mean by this is, this might be a bit confusing. What I mean by this, for every element that I can pick from Z plus, that is every positive integer, can be spanned by any one element of SC, because very simply, if I just look at these 6 numbers and if I try to think of it for larger numbers, I try to correlate with what's happening here. Every positive integer, when divided by 6, can have 5 possible remainders or be exactly divisible by 6. In that case, it's 0. So, every possible positive integer z can be represented as either it's a multiple of 6, or when divided by 6 it leaves a remainder of 1, 2, 3, 4, or 5. Now what's so special about 6? My property is defined with respect to 6, and hence I'm trying to bring in 6 in this form. I'm trying to form a basis of multiples of 6, basically, kind of like this. Hence I call the set S for 6. It stands for 6. So that's how I thought of it, that there's a basis to span C plus. Now why do I need to span the whole of C plus? I want to exhaust all the options, exhaust all the positive integers in C plus, so that anything I prove on this SC, anything I prove, any property I prove on SC, since it spans the whole of C plus, any property proved on SC will also be applicable to the whole of C plus. It's kind of the idea. So exclusion and exhaustion or exhaustion needs to be applied on these set of numbers. Now if I observe these numbers carefully, it's not too hard to know. These numbers, this basis is also again for Z, and it spans positive integers. It's got nothing to do with prime numbers, so it's got nothing to do with P here. But I started off with prime numbers. I'm talking about prime numbers. So in one way, I will have to observe the elements of the basis set and figure out how that is related to the set of prime numbers P. Now let's work on that. How are these elements related to prime numbers? So if you try to think about that, and I list down all of these options, sorry, bit of overwriting, looks like a sigma, 6n plus 5. So if this is 0 mod 6, it's exactly divisible by 6. It's already divisible by 6, so there is no question of it being prime, because a prime number doesn't have any factors other than 1 in itself. So this, I'll leave this for now. This can be written as, sorry, this, I'll use equal, because this can be written as twice to 3n plus 1. So regardless of n, for any n, this is identically divisible by 2. So 0 mod 2. Okay, so why did we bring in mod 2? The question has mod 6, not mod 28. This is to show that this number cannot be prime. So I excluded this number because it's divisible by 6. I have to exclude this number because it is divisible by 2. But is it just one number? Of course not, because this was a basis that spans C plus. So in other words, when I use exclusion, when I exclude some elements from this basis, it means that any number of this form in this basis, and that in turn spans multiple numbers in Z plus, that is to say that there will be multiple integers of this form, those integers can never be prime because they are divisible, they have factors, they have these factors. So this again has factors. This has a factor of 3, 2n plus 1, no luck. This is divisible by 3, so I'm writing it 0 mod 3. This basis can never span prime numbers, again, because it has a factor of 3. This again has a factor of 2. Now, here's just one factor visible here, depending on the value of n, because n can be any integer. Sometimes 2 can be the only factor, and sometimes there can be more common factors of this terms. But all we're saying is there's at least one factor dividing it, so this cannot be a prime number. This cannot be a basis to span prime numbers in C plus. And perfect. I eliminated all the 4 options except 6n plus 1 and 6n plus 5. And that means since this basis spans the set of positive integers, any prime number which is, now to think of it very clearly, and how we started off with, and how we started out with, any prime number p greater than 3, and that is a positive integer, so it will be a part of this set, and this set is spanned by these basis elements, and so for any prime number that has to be in this set, that has to be in the set of positive integers, because prime numbers is a subset of it, has to be spanned by some valid basis, and the only two valid bases are this 6n plus 1, 6n plus 5. So this will give us, since this is divisible by 6, this gives us 1 mod 6. Perfect. And this gives us 5 mod 6. And we are done. Are we done? Hang on a minute. There's one extremely important point. There's a scope for growing a misconception that any number of this form and any number of this form is a prime number. That, of course, is not true. You can see 6n plus 5. If I were to give you a counter example, let's say n equals 5, then 6n plus 5 is basically 6 times 5 plus 5. 5 is already a factor of this number, so this can never be prime. So this is very important to note. Not every number of this form will be prime, but all we are saying that if I'm given a prime number, if I already know that I have a prime number, the prime number will be of this form. So it's extremely important to understand how that mapping works. If I have a prime number, that has to be in the form of this or in the form of this, because all these 6 basis options, if I can call it that, these 6 basis options is a valid basis for the set of positive integers. I have a prime number that is a positive integer, so it has to be spanned by either one of these 6 options. And it has only 2 valid options it can be spanned by because it's a prime number. So if it's a prime number, it has to leave a remainder of 1 or a remainder of 5. But not every number that leaves a remainder of 1 or 5 has to be prime, because that depends on the value of n. Remember, this is a basis. This changes the spanning, or whichever number, whichever positive integer it represents in z plus, depends on n. So if n happens to be a number that gives you a composite number, not a prime number, that can of course happen. So while this will be valid, while this number still gives you a remainder of 5 mod 6, remember this number gives you a remainder of 5 mod 6. That's true. That's not the point. The point is this is not a prime number. But any prime number has to have a remainder of either 1 or 5 modular 6. It's pretty interesting, this one, and there are many interesting kinds of problems where this can be applied, and it really helps a lot. It usually helps a lot as a counterintuitive approach. Like if you're given a number and you see that it doesn't give you a remainder of 1 or 5 modular 6, then clearly it cannot be a prime number. That's always really useful. So thank you so much. Thanks for watching this video. Thanks for being with me. Thank you so much.